Hi class, today we're going to be looking at section 13.5 for our IM3 class. We're looking at applications of exponential and log functions. We're just going to do one example today. Your homework is very similar to this example, so you can watch this video a few times if you need to, but I think one example should cover it. All right, so in order to do this problem, we're going to be looking at a continuous compound interest problem. So the equation that we need to use for compound interest when it's compounded continuously is this A of t equals P times e to the RT power. P represents the principal or original amount in the account. R represents the annual interest rate as a decimal. E, remember, is a constant value. Let's see, if you plug E in your calculator to see what it is, E is approximately 2.718. There's more decimals there as well. And then T is our time in years. All right, so our first example here, our only example, is going to be that Edmund deposited $5,200 in a savings account earning 2.5% annual interest compounded continuously. So that piece of information here, compounded continuously, tells us that we have to use that formula. How many years would it take for his investment to reach $8,000? Show all work. So what we're going to do first is we're going to set up our equation with our A of t equals our initial amount, our principal value, 5,200, times E, and then our interest rate. Remember, we always want to write this as a decimal value of the percentage, so it'll be 0.025, so 0.025t. Now, this would be just using the interest rate and the principal amount in the equation. Now, we want to know how long it'll take to reach $8,000. So I'm going to replace A of t with $8,000 because that's how much I want to end up with in my account after t years. And I'm going to solve for t. Now, this is a little different than the other interest rate problems we've done because this is the first time we're solving for part of the exponent. And if you go back and if you haven't watched my previous lessons from this unit and the last unit in chapter 12, we talked about logarithms. And remember, the log is the exponent. So if I need to solve for the exponent, I'm going to need to use a log. Before we can use a log, we need to isolate this piece here. So I need to isolate this part here before I can use a logarithm. So my first step, I'm just going to rewrite my equation, 0.025t. So my first step in solving this is going to be to divide by 5,200 to get that e to the exponent by itself. All right, and if we plug that in our calculator, we get approximately 1.538. I would suggest using at least 3 decimals since we're still working with it. We don't want to end up with a large rounding error. All right, so now I have this. Now that the exponential piece, the base with the exponent, is by itself, the only thing we can do at this point is change to log form. I guess there's another way you could do this where you take the log of both sides, but we didn't really cover that. So the way I've been teaching it is change it to log form. So if I rewrite this in log form, I'm going to have the log with a base of e of 1.538 equals 0.025t. And if you remember back from our log formula, the log base e is a special log. It's called the natural log. And it's ln, and it has a base of e, base e. So if I have a log base e, I can rewrite this as ln of 1.538, and then it's just a little easier because I can use the ln button in my calculator instead of having to use the change of base formula. So I've got the ln of 1.538 equals 0.025t. I want t by itself, so I'm going to divide by 0.025. And then we can just plug that ln of, and make sure you close the parentheses after you type in the 1.538, then divide by 0.05, and t ends up being approximately 17.2. And then don't forget your units. We're looking for numbers of years here, so we want to include years. All right, and that is our example for today.